Welcome everyone for today's colloquium by Professor Uli Eriksson from Uppsala University. I will give a very brief introduction because of I think everyone knows Olli Hira, so as one of the leading figures in Swedish research, and Olli, like myself, worked in Uppsala University, so we share this connection to Uppsala. And so Uli also had postdoctoral experience overseas at Los Alamos National Laboratory, and now he had very broad research interest and very contributed to very broad list of topics. I will not be able to list all of them, but I will mention a few. Uli is famous for his work on magnetism, on various type of magnetic ordering, and with a large emphasis on various controllable numerical approaches, something which I personally appreciate very much, something with error bars and with concrete numbers. And now Uli also is co-chairing a large initiative, Wallenberg Initiative for Material Science, which is very important for research landscape here in Sweden. And I will not take much time out of his talk and keep this introduction short. And thank you very much for finding time to come here and to give us a presentation on this topic.
Thank you, Igor. And thank you all for being here. It's always nice to come here, and thank you all for showing up. So as you see, the title is maybe a rather grandiose one. I encourage you to follow me on this journey and think yourself, what is it that we who do calculations, materials science stuff on the computer, what you think we can not do also. I for sure the things that I show that I think we can do, I'm pretty sure we can do them. But I have one example of things we just cannot do. But if you can think of something else, I'd like to hear it. So you will see slides now in my presentation, and I have not generated a single result of these slides. It's all the result of a collaboration. If you now feel that you have contributed to this presentation and your name is not here, I apologize and let me know and I'll add it. My collaborations is my most important asset. The outline of my talk is as follows. I'll give, on Igor's request, a quick review of the basic ideas of density functional theory, and that is really the working horse for us when we do material-specific calculations. And so I'll go through that quickly, and then that leads us to the electronic structure theory, and I'll give you a quick review of that. You recognize this for sure. And then comes now a list of things we can calculate, and then an outstanding problem at the end. So it's an outstanding problem. I'll teach you with this a little bit. From an experimental side, it seems very trivial and easy, but from our side, it is at this point impossible. So density functional theory is what rendered Walter Kohn the Nobel Prize in 1998, and the basic idea that Walter Kohn is illustrated by these three fluffy clouds. So here's a space of densities, and let us focus this discussion on electrons. So this is now fermionic densities that you get from solving the Schrödinger equation, and you can do that in a fluffy cloud here that is labeled V space. This is the exact Hamiltonian as we know it if you do the Born-Oppenheimer approximation and you just solve the quantum mechanical problem for the electron system. So what Walter Kohn could show was that there is a bijective mapping between any Hamiltonian or any potential of the Hamiltonian, and therefore the Hamiltonian, to any density in this density space. So it's bijective, meaning, if you remember your algebra and geometry class, that no point here connects to more than one point here, and no point here is the origin of more than one point here. So it's one-to-one mapping. So that means that instead of identifying the Hamiltonian, which everyone can do, and then bracket that with the wave function and calculating the expectation value to get the total energy, you don't have to do that. You can work instead of electron densities because they define the whole problem. So that's Hohenberg and Kohn, and then Kohn and Sham said, wait a minute, if I now am only interested in the densities, why don't I then work with an auxiliary space of simpler Hamiltonian that are more tractable to finding solutions of. So that's now a many electron system, and this is now a one electron system. Here we know how to get the solution. And of course this mapping, the arguments that allowed this bijective mapping over here, it also applies here. So that means that that one can find a mapping, a bijective mapping between potentials in a one electron Hamiltonian of this green fluffy cloud, the one electron world, to densities also, and also from there calculate things you'd like to know, the total energy and things like this. So there's two statements that describes what I just said. The function exists that couples the total energy to the ground state electron density, the bijective mapping, and then there's also the variational principle works here. So the best approximation or the best density, if you have that functional, it's obtained by minimizing this guy with respect to the density, and you come as close as possible. Another way to say that is to say I have the fluffy cloud to the left, that's the real electronic Hamiltonian. I've now made the Born-Oppenheimer approximations. I'm left with solving the Schrödinger equation, or the Dirac if I like to, for the electron system, kinetic energy summed over all particles. I goes now over the Avogadro's number, so very, very difficult. The interaction between all electrons and all the nuclei, or again, the sum over things that are of the order of Avogadro's number. But if Ri now is fixed in a fixed position, this is also an easy one to do in principle. But the guy that we cannot handle is the electron-electron interaction, this guy here. So it's a double sum over pairs that involve the Avogadro's number. So that's the culprit of this problem. I have schematically now drawn red and blue to illustrate spin up and spin down electrons. You have to imagine that this is now spin up and spin down electrons, and this line here is the exact form of the interaction. So we know the interaction, of course, very well. It's an exactly known interaction, but because there are so many of them, Avogadro's number sums, we just can't do it. But the idea of Kohn and Sham was to replace the fluffy cloud to the left, if you remember, to the green fluffy cloud to the right, and that means replacing this system, this Hamiltonian, with this one. And so now one of these electrons lives in the one electron world. It lives in a mean field of all the other electrons, and I thought the mean field of blue and red would be a purple medium, so this now lives in a purple medium. And we are left with solving an equation that is a one electron equation. All of a sudden we don't have this 1 over Ri minus Rj. So formally this is exact. The only thing you have to do is figure out what this effective potential is in this effective equation. And another way to say that is to say what is the nuance of purple in this graph. That would be another way to say that. So there are of the order of 300 different nuances of purple, 300 different versions, parameterization of this this effective potential. There's only one formally exact effective potential. So the fact that there are 300 attempts is clearly a weakness for our field. It just shows that we haven't found the right one, and we'll never find the right one. We will find, or we have found things that are good enough for some things, but not for everything. So I solve this guy, I square the wave function, I get the density, and then I have moved my problem over to this world here. I have now figured out that I like one particular nuance of purple in this graph, one particular parameterization of this effective potential that gives me the right density. And since I don't have to now bracket Hamiltonian of the wave functions, I can simply calculate an energy density functional, then I can calculate everything I want. In particular, what I get out is the total energy. So that is your crash course in density functional theory, and the upshot of this is that it offers you a simple and easy way to calculate total energies of quantum mechanical problems. If you apply this for a solid, then things becomes a little bit detailed. You all know this. Due to the periodic lattice symmetry, the wave function has to have a particular form. It has a plane wave part and a periodic part. This is due to Felix Bloch's thesis work in 1928. This guy here is now a one electron wave function. It's operated on by this one electron Hamiltonian that we discussed, and then it gives back, operating the wave function gives back an energy and a wave function again. And that means that this index here, this crystal momentum that characterizes something of the order of, or something like the linear momentum of electrons as they move in the lattice. That is something that is a way to characterize the properties you get. So both the wave function and the energy eigenvalue of this equation here typically have a subindex or an index k here to indicate where you are in k space. Which leads to results that are as follows. This is now an example, the energy bands of BCC iron. So what has been done here is eigenvalues are plotted of the equation I just showed, and they're plotted as a function of k space, where the electrons are. The gamma point here is k equals 0, so then they have no crystal momentum, no linear momentum if you like. And then you can go through the Brillouin zone along different high symmetry directions back and forth here. And for each and every one of them, you make a selection for that k point and you solve the Schrödinger equation, and you get eigenvalues like so and so and so and so, and then you make the connection between them and plot these energy bands. So this now leads or gives us a tool to analyze the coupling between electrons' movement and their energies in the solid and their momentum. And so the crystal momentum is not really truly linear momentum, but it is connected to it. And this is something that you can also, many of you do this, is connected to experimental measurements. You can measure the energy dispersion, energy versus crystal momentum in an angular result photoemission study. So these energy bands can be mapped out and followed by ARPES measurements, and they never ever really agree. And I'll come to that at the end of this talk. So this is not something that really we can compare to experimental data. If it agrees, it's just luck, or it's not really supposed to be there. But with dynamic and mean field theory, and I'll come to that at the end of the talk, then these bands, these electron states can be squeezed and can be tweaked, they can be broadened in such a way that they finally start to look like what you find from an ARPES measurement. Already in the first papers that Kohn and Sham and Hohenberg wrote, they said, don't view these energy eigenvalues now as something that is experimentally detectable. It's just a Lagrange multiplier ensure that equations don't go haywire in the electron density. So it's just something that is introduced to make the particle number constant or not go out of control. It's the total energy, the energy of the functional that rules. And so this one is not so interesting. That's the one where you just looked at. This one here is the one that is the relevant one. Okay, but one can do at least a few things with this. Calculating the total energy is one thing, and many of my examples will be due to that. But one can also look at occupation numbers. And this is now for BCC iron. It's a system that spin polarizes. The functional itself favors an energy where there's an asymmetry between spin up and spin down particles. BCC iron prefers to have a little bit more spin up and spin down. And you can see it here. All electron states here now are filled up to a common Fermi level that's now at zero energy. This is now in electron volts. and the spin up is here, spin down is here, and there's an exchange splitting. You can see it maybe most easily at the gamma point. These two bands look like so. They are found over here, basically the same symmetry and shape of the bands, but these are now at a little bit higher energy than these guys here. This one is unoccupied above the zero line, and this one is occupied below the zero line. So there's an exchange splitting here of roughly 2 electron volts. So one can fill up electron states and to spin up and spin down up to the common Fermi level, and they say, okay, I know that the electron G factor is 2 in our world, and 2.00189, whatever mark you would say is in the real world, but in our world it's 2, and then you can deduce what the magnetic moment is of this material. And if I now do a plot, I make a plot of calculated and measured magnetic moments over a range of materials. It looks like this. Here you have the theoretically calculated, the DFT calculated spin moments, and here are experimental spin moments deduced from neutron scattering experiments or XMCD experiments or magnetometry, squid magnetometry. There's many tools with which one can do that. And so if the agreement between experiment and theory was perfect, they would all lie on a straight line, this line here. And you can see that this is now a carefully selected group of elements because they're all found to lie on this line. So here the agreement is very good. But it's not just luck, or it's not just something that I carefully selected and so there would look good or so. If one were to plot large groups of materials listed in, for instance, the International Crystallographic Structure Database, and would find the magnetic ones and find the non-magnetic ones that would be all down here, it kind of would look like this actually. So it's a really powerful tool to use, in particular in collaboration with experimentalists and experimental actors, in order to do something interesting to find functional magnetic materials, new windmills for new materials for windmills or magnetocaloric applications. So Fe2P is an interesting crystal. It has two crystallographic sites. One is tetrahedral, one is octahedral. If you look at where they are on this line, the tetrahedral one has a moment of roughly 1, and the octahedral roughly 2. Theory and experiment agree on that fact, and that's kind of good. It didn't have to be that. That's not obvious at all that it would be like that, but they both say that. This is a material that actually is the father of one of the more discussed classes of magnetocaloric materials used for cooling and as an alternative to our current cooling technologies, and with the potential of having much larger energy efficiency. The magnetic 3D, ferromagnetic 3D elements, iron, cobalt, and nickel are here, and also looks good, and the 4F element gadolinium is also good. So this is actually something that really works quite well. And it's also something that I like to do, and so I much of my experiments or results will come from here. There's another thing you can conclude from these kind of calculations, and that is what's shown on this graph here. So if I now look at the density of spin-up electrons minus the density of spin-down electrons, and I look at again BCC iron, but it doesn't matter what it is, any material would look the same. You will see that there are always red blobs and orange things that are close to the nuclei. Nuclei are here and here and here and here, and there's bluer regions in between. And so the redness indicates high spin density, so a large part of the magnetism comes from there. And the blueness means basically absent spin density, nothing much happens there. That means I can integrate this information up to a sphere, and if I do it here, or if I do it a little bit further in or a little bit further out, it doesn't matter, I still get the same value. And for iron I got the value of 2.2 mu b. And so that means I can replace this wave function based or density based information with this picture here. So just an atomic bar magnet with a north pole and a south pole, and the length of this guy then would be for iron two Bohr magnetons. So the picture of magnetism that we can then form becomes intuitive. This is what how we all think, and now this kind of shows that it's correct. There's a magnetic moment that's situated on one particular site, and it is very much localized around the nucleus of that site. You see now that these arrows are all drawn to be pointing in the same direction. It's a paramagnet in this picture. But of course, there are other materials that are antiparamagnetic or non-collinear or skyrmionic or so. So one may ask, why is that so? What differs? What makes them different? So that is something that also is a result of these kinds of calculation, and it's the result of work done by a very strong group in this field in Yekaterinburg in the 80s, and they said the following: if I have the Heisenberg Hamiltonian, and that's something that we all know, and I'll write it down in a second, how that describes magnetic interaction. And if I have two moments and I tilt them a little bit like this graph shows, I know how much energy that changes. Can I then calculate how much that energy change is also from my density functional? And if I can do that, I can find a way to map information from the density functional to a simpler Heisenberg Hamiltonian. And so this was done, and so the workers, the people that did this is Liechtenstein, Katz-Nelson, and then we jumped into this much later, Kvasnin, and we wrote a review article just last year. And it's not so important. I realize that not everyone wants to know all these details in this equation, but what this one shows is that you can calculate the exchange interaction, the strength of two atoms pairing up or pairing up parallel or anti-parallel is all given by this guy Jij. And it's written up as this equation here, the regular Heisenberg Hamiltonian. This is the strength of interaction. This one determines if something is ferromagnetic or antiparamagnetic. And this Jij is now calculated from a local exchange interaction that I get from these density functional calculations. So it's just exchange splitting, what we discussed for BCC iron, and then a Green's function, which is basically 1 over the Hamiltonian, Z minus Hamiltonian. And the expression is this guy here. So this means that it's okay, it's perfectly possible to do a calculation for something very simple, 1 atom per unit cell. And then it's very simple, very quick, very fast, no computational efficiency. And nevertheless get the information about exchange interactions in the material that go out as far as you want into the material. Nearest neighbor, next nearest neighbor. And so it's a very nice way to do a multi-scale calculation, to go from one scale to another. The scale of the electrons and 1 unit cell and so on, to a much wider ranged scale. And so we and others tried this, and so we calculated of this effective spin Hamiltonian everything, the interaction, the value of the magnetic moments. That was this diagram I showed a little while ago. And then you can subject this to Monte Carlo simulations and calculate magnetization versus temperature. That's shown here again for BCC iron. And so you see now that the specific heat, susceptibility, specifically this guy here, it has this sharp peak right where the simulated ordering temperature is, and that points to a critical temperature of around 1000 Kelvin, which is pretty much close to where the experimental ordering temperature is for BCC iron. So this is now a tool where I would say things we can calculate. We can calculate the size of the moments, we can calculate the ordering temperature, we can calculate the nature of the magnetic ordering, everything comes out. So it's basically a ready-to-use tool, I would say. And also we have been interested in using this to understand the spin glass system, for instance. And so it's really something that works quite well. But electronic structure theory and density functional theory is also useful for many other things, and so I'll try and give you a review of that also. So I spent most of my time on this one because that's kind of what I like to do. But I'll now show you a little bit how it works for structural properties, phase stability, lattice dynamics, superconductivity. I thought of Egor when I wrote that, and I have a slide for superconductivity. it's very relevant to understand metallic versus semiconducting applications, anything about microelectronics, quantum materials, heavy fermions, you name it. So when I started out my PhD work, then it was not so obvious what we could do and could not do. And one of the landmark things that Hans Skriver could demonstrate was that it's possible. There's enough energy there's enough accuracy in this approach to calculate rather fine details, for instance, as described by the crystal structure stability. And there are certain trends that are very clear and obvious across the periodic table. And Hans Skriver wrote a paper where he analyzed the structural stability of basically all elements of the periodic table, and he could pinpoint them all, reproduce the experimentally determined structure, with one exception: gold. Gold, what he found, was supposed to be BCC in this work, and it's of course FCC. And so this graph shows, I took this from his paper. It's for the 3D, 4D, and the 5D transition elements, and everything works out well except gold here. And then with a small fine adjustment to the accuracy of these calculations, then it was shown by us and others that gold also comes out to be FCC. So structural properties is fantastically well reproduced in this theory. And so we were very much interested in this in the 90s. We did a lot of calculations to be support to the high pressure community that really are looking at crystal structure stability as a function of applied pressure often in diamond anvil cell techniques and those kind of experiments. And we stopped. It got boring, in all honesty. We always reproduced or predicted things that then they could verify. It was basically not much challenge left in that. It was basically too good in a way. Yeah. So, but we had fun doing that for a while. That I have to say. So, crystal structure stability, equilibrium volumes, all comes out okay. Here comes maybe my favorite slide, because I can point to this very nice book by Göran Grimwall on the thermophysical properties of materials. Lattice dynamics. So if you can calculate lattice stabilities, maybe you want to also understand a little bit about phonons and lattice dynamics. So it's a well-known way to do that, and if you have forgotten how to do it, I encourage you to go and look here. What you want to have is to have an access to a pair interaction potential, and then you do a Fourier transform of that to get a dynamical matrix, and then you diagonalize that, and voila, you have the phonon frequencies. And typically then you get as a function of you get the frequency as a function of, again, a crystal momentum or information from reciprocal space, and that's the same K as you do in this Fourier transform here. This is accessible from measurements. I'll show you on the next slide how to do it. And the only the crux of the matter here is you want to get a hold of this force constant matrix, and the way to do that, well, you can do it in many ways, of course, but the way to do that from density functional theory is to simply calculate from a larger supercell the atoms in their equilibrium position, and then you move one atom a little bit up or down, and that brings the system out of equilibrium, and that induces forces in all other atoms in the system here, and that allows you directly to identify this phi here. So large supercell calculating forces in DFT calculations, and you have the phonons, and it looks like this. So this is what Petr Savatsis did 2008. So experimental data here is here as dots, and his calculations are lines. We have the 4D elements here: rhodium, palladium, and silver are FCC. Yttrium, zirconium, technetium, and ruthenium are HEP. We forgot to do the BCC for some reason. But you see that the agreement between experimental data and theory is actually pretty good. So that then led us to look into titanium, which exists in different crystallographic phases depending on temperature and pressure. And we were interested in try and see if we can understand, and we kind of knew that we could not understand the BCC crystal structure. It's stable at higher temperature, but then we subjected to the same machinery, the same calculations, same techniques that allowed us to do this. We then tried for BCC titanium, and then we got this. Now you should look only on the right-hand side, because the true answer comes on the left in a few slides, but now you should look on the right-hand side. And what you see is that for titanium and also for the isoelectronic elements, zirconium and hafnium, some of these modes are plotted to be negative. They're actually not negative, they're imaginary. And that means that the crystal is not even dynamically stable. It's not supposed to exist, it just falls apart. So something really came out wrong in this calculation, and it was not numerical or so, it was something fundamental. So we came up with something we called the scale procedure. Scale stands for self-consistent ab initio lattice dynamics. And the basic idea of this is that to say, no, it's not correct to just look at this force constant matrix for an ideally situated, perfectly crystalline crystal structure. Titanium is BCC at higher temperatures, and therefore the lattice is not a stationary lattice. The things are vibrating and moving around a little bit, and that vibration, that movement, that entropy, we thought, our working hypothesis is that stabilizes this BCC crystal structure, and that is what one have to take into account if one wants to have access to or be able to reproduce the measured phonon frequencies. And so we try to estimate how these, at any temperature, how these atoms are moving around. This mathematics here describes that, and I think I'll skip that and just show you instead what the results are. So now we go from the failure static lattice here to the dynamic lattice over here. And here all of a sudden the measurements, the black dots, actually are in pretty good agreement with the theory, which is the solid line. So all of a sudden, all these imaginary modes are gone. We can reproduce much of the measurements. We fail a little bit. This dip here, for instance, is not as steep as it should be for zirconium, but no theory is perfect. And so we were actually kind of happy with this. So I would say check on that also. That's also something we can do, lattice dynamics and phonons. Superconductivity, if you can do phonons, maybe you can also look at electron-phonon coupling and superconductivity. Now we go back to Stone Age theories for this, and I only brought it up because the person behind this is the Macmillan formula for superconductivity. The first person that would make a connection, that's at least as far as I know, a connection between electronic structure theory and real calculations of superconducting temperatures was this guy here, who we now all have heard about, I hope, Nobel Prize winner. So he was deep into electronic structure theory and microscopic understanding of superconductivity and other things also. And so he cooked up a way to connect the Macmillan formula to electronic structure theory by allowing to calculate this lambda parameter, which is then reflects the electron-phonon coupling. So this is something that only works for electron-phonon coupled materials. And you see his results here. So calculated, observed, 2, 6, 13, 16.7.7. So it's not so bad actually. But if one were to take this and also the more modern versions of these theories, you would never be able to make a plot with calculated and measured data with the same accuracy as we can do for magnetic properties. Superconductivity is a difficult thing for us to handle. So it's not a complete failure, but it's not as big of a success as the other things I talked about. So I will count this as some things we can calculate, but with the caveat that it's not perfect. Some of this system, well, I'm coming to an end actually. So some of the systems that I should say it like this: the systems that I've been describing so far are systems that are not trivial in any way. They have their complications in them, but they're not as complicated as some systems are. So there are certain things with them that stand out, and they are in particular characterized as materials where the mean field approach actually works out quite well, and there's reason to understand why that, or there's reason to believe why that is so, and that one of them is that electrons hop around in the lattice rather frequently. They are highly itinerant, and so they never meet a partner where Coulomb repulsion causes problems. But some materials have exactly this, and maybe there are those that would say that these are the materials that are maybe the most interesting ones. So nickel oxide is one, all the transition metal oxides, cuprate superconductors, many of the lanthanides, actinides. And here one needs to do something more. Here one needs to leave the purple effective medium, the effective one electron problem, and do something more complicated than that. And so I'll show that in the next slide. But this, the dynamic and mean field theory, DMFT, is the baby of Dietrich Vollhardt, 1989, and Antoine George and Gaby Kotlyar, 1992, that derived the DMFT equations that we all now use today. So that's a little bit of the founding fathers of this. And the basic idea is the following. It's not that complicated. Suppose I have now atomic nuclei positioned in the lattice like this. And suppose now that this green dot that I'm shining with now, it represents an electron. So it's following quantum mechanical laws of motion. Maybe it spins around here for a bit, it jumps over. After all, this is an itinerant electron system, or semi-itinerant. Spins around here, and then maybe comes to this site here and stays there for a bit. Okay, suppose that during that time, another electron came from up here, and it moved around, came here, and then it also moved around and stays on the same site. And if there's two electrons on the same site and they stay there for a bit now, then this whole DFT idea, the whole mean field approach breaks down. Because there's Coulombic interaction between two electrons that are rather close in space, and so they will simply see each other. Mean field approach won't work. So mathematically one has to then say, I take my Kohn-Sham Hamiltonian, my LDA Hamiltonian, and I add to this Hamiltonian the fact that every once in a while two electrons are at the same site, and that's what this term here is supposed to say. And U is now the energy with which that interaction is. And that U value can be anything between 2 electron volts to maybe 10 electron volts, depending on material. That system, that problem, that Hamiltonian is impossible for us to solve. At least I don't know how to do it, and a lot of people have struggled with it. But what the DMFT idea is, it says I don't have to take this, look at this complicated problem. I can look instead of pulling out this central atom and put it over here. And then I said the most important thing is not if the one electron came and jumped from here to here and the other one came from here and here. The most important thing is that every once in a while electrons jump on and off this Hamiltonian or on and off this site, and that costs an energy U. That's the most important thing. And that means that the problem becomes an impurity one. I allow now electrons to jump off and on this site, and it jumps off and on into orbitals in this fluffy cloud, and that's now representing the whole lattice, the dynamic of the whole lattice. It's not at all obvious that that can be done, and so that was one of the achievements of the DMFT people to show that can be done. But it was shown, and once you have that, then this is a system for which there are solutions. This is the Anderson impurity model, and so there are solutions to that. And so instead of going into the details of this, let me show you how this works. Here is an example that we were interested in. This is the terbium-indium copper 4. It's a mixed valent material. That means that the terbium atom doesn't know if it's 2+ or 3+. It's somewhere in between plus. And there are measurements, Hackspeth measurement on this material. that's plotted over here. One were in the experiments, one were able to extract what came from copper and indium to identify what was the contribution of the 4F shell. And don't ask me how that was done, but they did. And then they came to this experimental spectrum and said, this is now the spectrum that comes from the 4F shell of the ytterbium atom in this compound. So this is something that is occupied states, so Fermi level is a 0, you don't see in Hackspace anything that's unoccupied, and there are electron states that can be kicked out from this material with the binding energy down to almost 12 eV or so. If I now took the conventional DFT eigenvalues and pretended I ignored my own warning that I started this talk with, and I said I ignored the fact that there are not really anything I can compare to experimental data. I do that anyway. Then I get this narrow band here. So that's the 4F contribution from regular DFT calculations. So this agrees terribly with what's over here, right? But DMFT then tweaks this narrow peak into what you have up here. So this is DMFT in a particular approximative way to do it. And so you have the two-peak feature here. You have things that go down to 12 eV. You have a gap in between. You have a gap in between. You have 3 guys here. You have 3 guys here. It actually looks pretty good. It certainly fixes things up much better than just looking at this and say, we don't know how to do this. Nickel oxide is another one. So here is now measurements of inverse photo emission. That's this graph here above 0, and photo emission, XPS, these points, round circles here. And theory now is the solid black line. Nickel d orbitals is black, and oxygen P is red. And the sum of this actually starts to look pretty good, and a pretty good agreement with experimental data. So I'm coming to an end, so a lot of things can be done if you are an experimentalist and you work in the solid state world, and if you don't have a friend in the theory department that can do these kind of calculations, I pity you. This is my message is try and find such a friend. It really helps your world a lot. And also helps us to tweak and fine-tune our theories when we interact with experimentalists. So that, I think, is maybe my main message. But now I come to the failure that I promised, and so which is something that I would love to be able to do, and many of my experimental colleagues would also love for us to do, but we cannot. And that's represented here. So if you're in the business of finding new materials, the first thing you do is you look at the phase diagram, what has been done before. And so typically it's in ternary phase diagram, and this one is particularly delicate and complicated. It's silicon dioxide up here, calcium oxide down here, aluminum 2O3 here. It's a phase diagram I think very often used or relevant for people who are interested in glass and high purity glass. This is now a phase diagram that has been identified by experimental means. You mix, you stir, you cook, and anneal for a long time, and then you do X-ray diffraction, and you say, oh, okay, it's corundum here. So very time-consuming, very accurate measurements has to be done. Of course, it would be fantastic to be able to do these things from DFT and do these kind of calculations to maybe point to, well, there's a little pocket here that you have missed in the experiment, and so sorry, that you should look. There's not the phase right here, but the accuracy we have in these functionals, the accuracy we have in these calculations, are not good enough, not by a long shot, I would say, to even be close to be relevant when it comes to identifying and looking at phase diagram like this. And so from my point of view, this is the most challenging thing we stand in front of now, our community, the DFT community, or the practical material specific calculations of materials community. And so I leave you with this comment, this conclusion, and thank you for your attention.
Questions?
So you compare the DFT density of states, and as you pointed out, there's no reason that this should look like the spectra, and then you compare it to DMFT, where you have some sort of frequency dependence, and it makes more sense to calculate actually excitations.
Yes.
But wouldn't the fair comparison be to do time-dependent DFT and compare that to the experimental data? And is there a sort of systematic?
Yes, and so that's right. And so if it was a weakly correlated system, then you get pretty good agreement with experimental data. That's a good point, Alexander. But you would never, with the TDDFT, make this guy go into this. I doubt it.
But has this been carefully studied?
Not that I know. But then you would say, well, every once in a while in the TDDFT, then the wave function visits then a configuration that will correspond to something down here, and it would evolve like that. And so maybe formally it should work, but practically I don't think it would work.
Because strictly speaking, DFT is actually exact, right? It's just a matter of.
But in the TDDFT world, yes, not the regular static DFT world.
Yeah.
Can I ask a question about magnetism?
Yes.
You showed for iron that the polarization is very localized.
Yeah.
How do you get exchange if there is no spin polarization interatomically? Or is that put in phenomenologically?
No, because if you look at the exchange and correlation functional, if you look at the total energy, the DFT functional, it has in it the kinetic energy operator, it has the Hartree operator, Hartree functional, and it has an exchange and correlation energy. So this one is the most dominant term of this guy is the density to the power of 4/3. And if you can, an exchange is in its nature such that it favors parallel spins, right? And so, and this term here also understands that. So just like in Hartree-Fock theory, where you can easily see that exchange interaction favors parallel spins, this guy also understands that. And so the reason why iron is magnetic and aluminium is not is that in aluminium, this term also would favor parallel spins of the P band, SP band of aluminium. But the penalty of having a lot of exchange splitting is that the kinetic energy then is increased. And so there's always a balance between the kinetic energy, electrons like to hop around on a lattice, versus being spin polarized. And so if I now go through all the elements in periodic system, all functionals, all 300 nuances of purple here, all 300 effective potentials, all 300 versions of the exchange correlation energy, they would faithfully reproduce that iron, cobalt, and nickel should be spin polarized, whereas the ones that don't spin polarize should not be spin polarized. So that actually comes out okay.
So the exchange energy is obtained.
It's in here.
Exactly.
It's in here. It's in here. Anders?
Wonderful talk. We'll learn a lot from this talk. But can you put up this ytterbium case once more with the Huggs-Bess? And as you know, we measured many of these things when we were both graduate students in Uppsala. And then we often thought about these spectra that, if I remember correctly now, the final state where you say 2+ is an F13, right?
Yes.
It's simply the spin-order splitting that you have, and the other one is F12. So how much can you actually describe this with the atomistic just multiplet splitting?
This is basically an atomistic multiplet. A fingerprint of an atomistic multiplet feature. So this is basically atomic physics. Yeah, it is. And the reason is that the ytterbium, as you know, does not hybridize so strongly with its surroundings. So basically it's a localized atomic picture on each site. So that was not to do with this, of course, because that was known already. But the fact that we can tweak something that looks so poorly into the correct domain, that was for us the most important thing.
Thank you very much. I wanted to ask you if you think that development of quantum simulators will help you develop the theory.
Say that again.
If the development of quantum simulators will help you with your theory to develop it.
Yeah, a lot of the work of quantum simulators and optical lattices and things like this becomes basically a question of an Hamiltonian that is the same as this guy. You have some kinetic energy, something hopping around, and then you have a Coulombic repulsion. So it's there's a lot of overlap in the physics between those systems and these correlated electromaterials. Absolutely, a lot of overlap, really. So I maybe if we're running out of the questions, then I have two conclusions. Experimentally, you should. Okay, we're not. Yeah.
Maybe I'll try to shout. I guess why DFT fails in the phase diagram is because the energy differences are very small between the different phases. Can you put a number on that? Like how accurate is DFT in energies? I mean, like what's the typical failure for energy?
So in some ways, you know, the changes in the energy, for instance, when you calculate elastic constants, something we also amused ourselves with doing, then you have to be on a micro Rydberg level. So that's very delicate, and there we were okay, and other people also. But then it was a change. So it's just if I distort something, I change something that cannot okay. But in this case here, you have to not only look at the change, but you have to look at what is the free energy, total energy of this guy compared to this guy, compared to this guy, which is different than say I take this phase here and I tweak it a little bit, I rotate a little bit. That's easier for us to understand. But here, of course, is a free energy in phase space, configuration space, concentration space. You reach a minimum, and that describes that this phase is the same. You should compare that to the competing phases, of course. If you can break this one up into a little bit of triminite and this red guy, and I wish I had an answer to your question. I think it's of the order of milli EV or less than milli EV that we need to have per unit cell here, and it's just not there. It's just not there. We have Lars and then Anders.
So I really need a microphone, but I'll try. Staying with this phase diagram, how many dimensions do you have? You have composition. Up at the top, you have two liquids.
These are this one I don't know actually. This is at some it's at some temperature. So at some temperature, this will become some of these phases are liquids. But don't look so much at this launch. It's just these points here, or these areas, they're identified by stoichiometry, a given stoichiometry, and a given crystal structure.
But it should really be multidimensional if you have both composition, temperature, pressure.
Yes. And so this will change with pressure and with temperature, and no matter what temperature and pressure you select, I will fail in reproducing it.
Well, it becomes even more challenging.
Even so, yes, even so. Anders.
I think if we, I will speak up, if we will go to a more simple, let's say even simple system, but weakly interacting, I wonder how DFT could reproduce the phase diagram.
Yeah, but Anders, these are uncomplicated systems. There's nothing strongly correlated here. So this is as simple as you can get from an electronic structure point of view.
Yeah, but just take a water molecule.
Yeah, okay.
and you have floating crystalline phases of ice. You know,
Yes.
the phase diagram
Yeah.
of ice is
Yeah.
a very difficult computation.
Yes,
to produce.
yes, yes.
So there
Yes.
you have even homology.
Yes, that's right. That's correct. That's maybe one more example where theory struggles a lot because it's really a difficult material. Yes, I agree.
Maybe if there are no more questions, maybe I
Yeah, I want to have the final word though, but you say something first.
just one question I wanted to ask. Like if one looks at generalizations of these methods or these methods, the class of these methods, was something done on the following problem. It has been observed for a long time that superconductors in crystals with twinning planes, sometimes superconductivity is enhanced on twinning planes, sometimes it is suppressed, and it's typically handled in theory papers purely phenomenologically. Like other, do you know if ab initio works were done, like if it's possible to do with these methods that like some
To microscopically say something about superconductivity and transient.
Superconductivity around crystalline defects. If crystal is non-perfect,
Yes.
there's twinning plane,
Yes.
for example, like what are the modes on twinning plane?
Yeah, I actually I don't know that. I'm sorry, I don't know that. But the theory of from the methods to from theory calculate superconductivity has been improved a lot since these works. And I mean, 1969. It's some time ago. I just wanted to show that John Hopfield was early with these kind of theories before he went into the machine learning and neural networks and stuff like that. But again, we are not as good, or the people that do this using DFT and DFT-based theories are not as good in producing calculated values that agree. This is, I think, is a little bit of a lucky comparison. Looks pretty good, but but in general, it's not that great. However, some of these hydrogen sulfur-based systems that are rather controversial, but have been reported to have critical temperatures close to room temperature, in particular under pressure. They were, I'm pretty sure, were identified by theory, density functional theory, electronic structure theory before the synthesis was made. So it was at least inspired by theory, if nothing else. Okay, so that leaves me with a final word, and that you should all go home and look at this book here. So.